Hello, this video is about exact differential equations, its definition and examples. Exact means accurate, correct. Yes, that means some differential equations are exact and some are not accurate, some are not correct. Confusing, no? Isn't it? Let us see why some differential equations are called exact and why others are not exact, others are not accurate. This exact differential equations is the third type of first order differential equations. We have already seen the differential equations which are in variable separable form and which we can reduce to variable separable form. Now we are going to see exact differential equation. In this presentation, we will see the definition of exact differential equation and the condition which helps us to determine whether the given equation is exact or not, and some examples of exact and non-exact differential equation. Consider these two differential equations, xy dash plus y equal to 0 and xy dash minus y equal to 0. Both are very simple and similar differential equations. The only difference is of sign. Here it is plus and here it is minus. This is nothing but y dash is equal to minus y upon x and this is y dash is equal to y upon x. They are in variable separable form. Integrations are so simple. So just solve them and check your answers with this. The solution of first one is xy is equal to c and solution of second one is y by x is equal to c. Okay. Now this is my function which is equal to constant and which is solution of this differential equation. Let us differentiate these two functions with respect to x and let us see what happens. So d by dx of xy, I am differentiating this implicit function with respect to x. So it is x into derivative of y with respect to x, that is y dash, plus y as it is, derivative of x is 1. And differentiating this with respect to x, we have to apply division rule. So it is x as it is into derivative of y with respect to x, that is y dash, minus y as it is divided by x square. Now observe the things carefully. This derivative of xy with respect to x is nothing but LHS of our differential equation, xy dash plus y. And here it is not exactly the LHS of our differential equation. That means here derivative of this function is nothing but xy dash plus y and my differential equation is that is equal to 0. That means in short my differential equation is derivative of xy is equal to 0 and therefore xy equal to constant is solution. Here I can't say that this equation is exactly derivative of this function is equal to 0. See one thing, if I equate this term with 0, then this x square will get cancelled because I can multiply by that x square to 0 which is again 0 and I get this differential equation. But this is not exactly same as derivative of y by x is equal to 0, but it is in fact simplified form of that derivative of y by x is equal to 0. And here it is exact form of derivative of xy is equal to 0. So this equation we call as an exact differential equation and this is non-exact differential equation. Both are very similar, both are very simple, but one is exact and other is not. Okay, but we can't define like this. That means if the differential equation is expressed as derivative of some function equal to 0, and it is exact form and not simplified form, like here it is exact and here it is not, it is simplified. This is not the way to define something. No, we want to define it precisely. So for that matter, let us explore these examples further. If I define this function xy as a function of xy, function of two variables, then I know that the derivative of this function, total differential of function of several variables. Here it is function of two variables. So this total differential is dabba f by dabba x into dx plus dabba f by dabba y into dy. If you have any doubts regarding this, just visit the corresponding video in multivariate calculus, which is calculus of functions of several variables. You can get this there. df is equal to this, but for our function f of xy equal to xy, dabba f by dabba x is y and dabba f by dabba y is x. Partial derivative of f with respect to x, that means differentiate with respect to x keeping y constant. And same is for dabba f by dabba y. So dabba f by dabba x is y and dabba f by dabba y is x. So this df is nothing but y dx plus x dy. Now my differential equation is xy dash plus y equal to 0, means it is x dy by dx plus y is equal to 0. Multiplying throughout by dx, I will get x dy plus y dx is equal to 0, which is this x dy plus y dx. And we can do that. In fact, while separating the variables and solving the differential equation using that technique, we always separate dx and dy at LHS and RHS, isn't it? So, this is the same differential equation, but it is now total differential of this function f, and the coefficient of dx is partial derivative of that function with respect to x, and coefficient of dy is partial derivative of that function with respect to y. So, in fact, my equation A is nothing but this y dx plus x dy equal to 0, but this is nothing but derivative of xy. So I am getting derivative of xy is equal to 0, and therefore my solution is xy is equal to c. Let us check whether it is true for our second equation in B. So equation in B, if I want to write it like this, multiplying by dx, I will get minus y dx plus x dy is equal to 0. And my function is y by x, that is our solution. So let us check what is dabba f by dabba x and dabba f by dabba y if f is equal to y by x. If f is equal to y by x, dabba f by dabba x is minus y by x square and dabba f by dabba y is 1 by x. And coefficient of dx is not this and coefficient of dy is also not this. So I cannot express this as df or total differential of this function, and that's why it is not exact. So I am getting towards the definition that if we represent our differential equation in this form, that means some term into dx plus some term into dy equal to 0, and in that case, if coefficient of dx is partial derivative of some function with respect to x and coefficient of dy is partial derivative of some function with respect to y, then this is nothing but df equal to 0. Total derivative of that function is equal to 0, and then it is exact. But for that matter, is it true for this form only? No, because any differential equation we can transfer into in this form. In fact, it is another general form of writing first order differential equation. I will explain that form first with standard notation, and then we will define exact differential equation. Now we know that a general form of first order ODE is y dash is equal to f of xy. The ODEs in our consideration is y dash is equal to f of xy. So, multiplying this f of xy by dx, I can write the differential equation as f of xy dx minus dy equal to 0. If this function f of xy is rational algebraic or rational function, that means some denominator is there and numerator is there, multiplying by that denominator, in general, I can write this as some function of xy into dx plus some function of xy into dy is equal to 0. And standard notations for these two functions are m and n. So in short, we call this form as m dx plus n dy equal to 0, where m and n are functions of x and y. And for any differential equation, we can transfer it from form 1 to form 2 or from form 2 to form 1. For example, consider this. This is my differential equation in form 1. Then y dash is nothing but dy by dx. So by cross multiplication, I will get xy minus 2 into dx minus this x plus 3 into dy is equal to 0, which is my form 2. Here my m is xy minus 2 and my n is minus of x plus 3. Now my differential equation is in this form, considering that, assuming that we can define the exact differential equation as if m and n are partial derivatives of some function, we call it as exact, and that is our definition. A differential equation which is in the form m dx plus n dy equal to 0 is said to be exact if there exists some function f of xy equal to c such that m is its partial derivative and n is its partial derivative with respect to y. Since these are partial derivatives, there is no need to say that these are exact partial derivatives and not in simplified form, etc. Because we are talking about m and n and not in the equation with equating it with 0. So there is no need to say that this is exact and not in simplified form, etc. So this is the definition of exact differential equation. Now, if it is exact differential equation, obviously, if m is dy by f by dy by x and n is dy by f by dy by y, this complete term in LHS is nothing but total differential of f. So df equal to 0 is the reduced form of this differential equation if it is exact. And since this is my differential equation, obviously its solution is f of xy equal to c. Now let us see some examples. As in our previous example, xy dash plus y, that is y dx plus x dy equal to 0. This is partial derivative of xy with respect to x. This is partial derivative of xy with respect to y, and it is an exact differential equation. We have seen it already. Our second equation is not exact, because we have seen that minus y and x are not partial derivatives of any function. In fact, its solution is y by x and they are not partial derivatives of that function. Now you can get one point that for saying something is exact, we have to produce one function. But for saying something is not exact, how can we say that there does not exist any such function such that this is true? For example, consider this differential equation. Y dash minus y equal to 0. It is very simple differential equation. Y dash is equal to y. For which function its derivative is itself. It is exponential function y equal to e raised to x. Verify that y equal to c e raised to x is the general solution of this differential equation. But without considering this solution, can you say that this is exact or not? In fact, it is y dash minus y is equal to 0, means it is minus y dx plus dy is equal to 0. And how can we say that there does not exist any function for which these are the partial derivatives? That means for determining whether a given differential equation is exact or not, we have to find its solution first, like here or like here. And then by finding partial derivatives of that function, we can say that it is exact or not. But that is not the case. If such thing is there, how can this concept of exact differential equation help us in solving differential equation? Because for determining itself, we need a solution. That is not true. Some condition should be there so that we can check whether a given differential equation is exact or not. In the next video, we will determine that necessary and sufficient condition for a differential equation to be exact. And we will also solve some problems using that condition. If you like the video, subscribe the channel, share it with your friends. Thank you.